All right, great. So my name is Clint Kelly, and here tonight to talk to everybody about Kiji. Kiji's an open source platform that lets you more easily build real-time big data applications on top of Cassandra. So to get started, the agenda for tonight, I'm going to begin by describing the problem that the problem that we set out to solve when we were developing Kiji, namely building a big data application. I'll talk a little bit about what it means to build such an application. Afterwards, I'll talk about how Kiji works, what some of the components are of this framework, and how it enables you, or how it enables all of us as Cassandra developers to more easily build these applications. Then finally, I'll talk about the Kiji data model and how we map the Kiji data model on top of Cassandra. So first, a little motivation for Kiji. Let's say that you want to build a real-time big data application. I've given a few canonical examples of such applications here. To be a little bit more concrete, let's say that you work at a retailer, somewhere like Best Buy, and you want to enhance your website such that you offer more personalization to your customers. Maybe you want to offer personalized product recommendations, for example. So how would we go about personalizing recommendations? Well, to begin with, we can look at what customers have added to their shopping carts. Let's say that we have a customer, Jane, and maybe Jane's just put an iPad in her shopping cart. It makes sense then to recommend to Jane that she buy maybe an iPad case or some cables, something like that. Furthermore, if we see that Jane spends a lot of time on our application looking at product reviews, we'll probably want to further personalize these product recommendations for Jane by offering her iPad cases that have 5-star reviews. Likewise, we can look at whether she's applied a lot of filters for the prices of products, what kind of items or what sort of searches she's performed on our application. And we can also look at how she or any other customer has interacted with the mobile version of our application. All of these methods provide us ways to give our customer a better personalized experience and to provide better recommendations. So that's a quick example, a little bit more concrete of what we mean by one of these personalized big data applications. So how do we go about building these? A good place to start is with a lot of the great open source software projects that are available out there. There's a lot of great stuff. It's very scalable and designed for these kinds of applications. To begin with, we need a way to store all of this data about how customers have interacted with our application. And as we all know, as Cassandra users, Cassandra is a great source or a great option for storing this kind of, this vast amount of high volume, high velocity time series data. Once we have all this data in Cassandra, we'll need a way to perform some computation on it. And again, a natural choice for this is Hadoop. And then beyond these, there are a number of other open source software projects in this ecosystem that can be really helpful for us building this application. Fortunately, we have companies like DataStax who provide us with enterprise-ready, certified collections of these applications that we can use, these open source software projects that we can use to get started. So now it's really up to us to take all of this open source software and go from that to this final real-time big data application. So let's look at exactly what we need to build to build this bridge between those open source projects and our application. To begin with, we need a way to get information about how our users are interacting with our application or our shopping site into Cassandra. We could design our application such that we record user interactions into flat log files or into relational databases. If we do so, we can then use Hadoop to bulk load all of this data into Cassandra. A more elegant way to design this application might be to use some kind of REST interface. This would enable us to store all of the data, or excuse me, to record all of our user interactions with our application in real time. So immediately as someone's adding something to a shopping cart or applying or performing a search on our website, we can store that data into Cassandra immediately. Once we have the data in Cassandra, we'll likely have some data scientists on our team. And the data scientists are going to want a way to query the data we have in Cassandra using languages that they're familiar with. Data scientists are usually quite comfortable with SQL. So we might want to develop a pipeline that lets our data scientists use a tool like Apache Hive to read data from our database. Once they've gotten data out of Cassandra with Hive, they might then want to use some pretty standard data science tools like R or Python to analyze this data, gain some kind of insights about how customers use our application, and then apply those insights to develop some kind of predictive or machine learning model. Once we have one of these machine learning models, we need a way to train it. Train machine learning model. So as everyone who's used these kinds of models is familiar, typically we want to train this model over all of the data we have in our database so that it'll be better able to predict how customers are going to behave. It's natural for the data scientist to wish to train these models using the familiar tools R and Python. But as I'm sure many of you know, R and Python don't really scale out to the vast amounts of customer data that we can store in a database like Cassandra. A better choice then would be to do all of our model training using Hadoop. Hadoop is super powerful and very flexible, but unfortunately it's not the most accessible technology, especially again for a data scientist. So we'll likely want to provide some kind of a mechanism for our data scientists to train the machine learning model based on all of the customer data we have in Cassandra using some kind of tool that attempts to kind of bridge this gap between the accessibility of something like R and Python and the power of doing in-Hadoop analysis. So there are a number of, again, these open source projects that attempt to bridge this gap. I listed a couple here, Scalding, Spark, and Cascading, but there are loads of others. As a quick aside, when we talk about a model here, we can think of it as a function. The function's input is all of the information we have about a given user. So this includes all of the up-to-the-minute time series data we've recorded about everything a user has viewed or clicked on or purchased. And the output of this function, in this case, is a set of product recommendations for our customer. But it could just as easily be any other kind of derived insight about one of our customers. It could be perhaps an estimation or an estimate of whether if we offer a given customer free shipping on an item, that will lead to a conversion, for example. OK, and this model could typically consist of some Java and Scala code. But we could also use some kind of an XML-based representation of a model, something like PMML, which if you use R, for example, you can export any trained machine learning model into PMML. In any case, once we have one of these trained machine learning models, we now want a way to apply it. In the case of our example here, we want to apply it to determine the product recommendations that we wish to provide later for all of the customers in our shopping website. So one way we could go about doing this is to use Hadoop. We can pretty easily write a Hadoop job that will read out of Cassandra all of the data that we have about all of our users, and then apply our machine learning model over all the data for all the users to generate product recommendations for all of the users. And this will give us these derived customer insights or recommendations for all of our users in Cassandra. But there are a number of downsides of doing this kind of a batch operation. We'd probably do this only once a day or maybe once an hour. And so this means that when our application later wants to retrieve generate these product recommendations for a given customer, they'll likely be a little out of date because they won't reflect all of the ways that the customer has interacted with our application since the last time this batch job was run. Also, if we're building something like a shopping website, typically most of our users are only going to interact with the site maybe a few times a year or a few times a month. And so if we constantly run these batch jobs over all of the users of our application, they're wasting a lot of computational resources too. And I'll describe in a minute how we can address these problems. Finally, we need a way to get data out of our database and back to our application. The REST interface that I described earlier is a good mechanism for doing so. All right, so let's review what we've described so far and how it works, how it all ties together. So let's say that we have a customer, and he's using our shopping website. He clicks on a link that takes him to a web page that has some real estate reserved for product recommendations. When he does so, our big data application will talk to Cassandra over REST and say, give me whatever product recommendations our machine learning model has generated for this given user. Cassandra will send the data back over REST, and the application will then render these recommendations on the screen. So this system works, but again, we have those shortcomings of a batch operation leading to a lot of recommendations that could be out of date. So how can we do better? Let's say, again, that we have a user interacting with our big data application, our shopping website on his computer. He clicks on a link. It takes him to a page that has some room for recommendations. Our application makes a request via REST to Cassandra for recommendations to show for this customer. Now, however, we add some application logic around Cassandra. And this logic sees this request coming in for a new recommendation, and it will immediately kick off a real-time application of our trained machine learning model to generate one of these recommendations on the fly. By doing this, by only executing this machine learning model now, we ensure that the product recommendations that we're writing back to Cassandra and then serving to our application are based on the most up-to-the-second latest information that we have about how this user has been interacting with our site. And also executing one of these models is pretty quick, and it's easy to do so within the latency requirements of our application. So after doing so, Cassandra sends the recommendations back to the application, and the application renders them on the screen. And the user sees wonderful product recommendations. And oh, sorry, you have a question?
What is your latency requirement?
I don't know, does somebody else from the team want to answer that?
Milliseconds is one of the numbers we have from one of our customers. So it's going to be there about 150 milliseconds plus minus.
Yeah, so the question was, what do these latency requirements look like? And the answer is typically on the order of 100, 150 milliseconds.
So the model has to be executed in less than 150 milliseconds.
Applied, yes.
Yeah, so training the model will take a really, really long time, but actually applying it is usually super quick. All right, one other thing that we need to build for this big data application is we need a way for our data scientists to run different experiments. Our data science team is probably going to have lots of different versions of these trained machine learning models. They'll have different models for serving different kinds of recommendations or other predictions we want to make about our customers. And for each of these different types, they'll have multiple variants. They'll probably want to run some A/B testing and determine which ones are the most effective. So we'll need a way to manage all these different models, and we'll need a pretty elegant way, or hopefully a very elegant way, to deploy these models and bring them on and offline without having the data scientists, without a lot of latency. So in summary, there are three main kind of categories of functionality that we need to build. First, we need a way to get data in and out of our system. And again, doing so versus REST is probably the most elegant way to go about this. Second, we need a way for our data scientists to be able to inspect the data that we've stored in Cassandra. Then they'll need a way they'll look at this data, gain some insights, and then want to develop and train some predictive or machine learning models. And finally, we need a way to apply these models, preferably in real time, so that we can provide recommendations or other insights that are as fresh as possible and based on this up to the second time series data we have about all of our customers. So that hopefully gives you a good overview of some of the major components that we need to build to go from all of these open source technologies to our final real-time big data application. And this is a fair amount of work. You can build this, but it'll probably take a fair amount of time, and you need a reasonable sized engineering team. And with this in mind, we've developed the Kiji Project with the idea that it should help all of us as Cassandra developers to more easily build these kinds of applications, and really to get a head start and avoid kind of reinventing the wheel with a lot of this functionality, and instead be able to focus more on what differentiates our application and what makes it special. So hopefully that gives everyone a pretty good overview of the problem we're trying to solve and why we built Kiji. Now I'll talk a little bit more about how Kiji works and how the different components of Kiji allow us to build these applications more efficiently. First, a little historical note. So we developed Kiji at WibiData. We're a startup company in San Francisco. That's where I work. We have 40 employees. Kiji was founded in 2010 by employees from Cloudera and Google. And these are folks with a lot of experience building these kinds of applications and who really enjoy doing this and were interested in providing a way to solve the problems I just described. There are also people with a lot of experience with open source big data technologies like Hadoop and HBase. And finally, we've added, since the company was founded, we've added a lot of other folks from companies like Amazon and LinkedIn that are also in this space. In 2010, when we started the company, we originally built Kiji on top of HBase and Hadoop. This was a natural choice at the time. Cloudera offered excellent enterprise support for HBase and for Hadoop. And HBase is also integrated very nicely with Hadoop. But since then, at WibiData, we've seen a remarkable amount of customer demand for a version of our software and Kiji that runs on top of Cassandra. So this year, we've added support. We've updated Kiji such that it's capable of running on top of Cassandra as well as HBase. One other thing that's pretty exciting, we have Kiji in production now. So there's one Fortune 500 retailer who's using Kiji for pretty similar application to what I just described, serving real-time recommendations to users for products. Also, Opower, who recently went public, uses Kiji for logging time series data about energy usage, and then using it to generate statistics and reports. Yes?
How long has it been on the market?
So we just built the Cassandra version this year. I'll talk about the project status a little bit later, but it's not fully developed yet. So now I'll discuss a little bit about how Kiji works and how the different components of this modular open source platform can enable us to more easily build these kinds of applications on top of Cassandra. So at the heart of Kiji, we have a storage system. The storage system kind of sits between the engineers and the data scientists in your organization. For the data scientists, engineers typically care about ways to write data to Kiji and ways to read it back. And the most important thing to them is usually having very clean, consistent, stable APIs for doing so. Where data scientists want a way to be able to query data from Qiji, and then to analyze this data and use it to gain some insights and then later develop and train some machine learning models. For the engineers, we provide APIs for writing data into Qiji. This data could come from different versions of our application running on various platforms. If we design our application such that we record user interactions with it into flat log files or into relational databases, we provide a component Qiji MapReduce that we can use to bulk load this data from these logs and databases into our storage system. As we discussed earlier, possibly a more elegant approach to building such an application is to use REST. So to this end, we provide Qiji REST. Qiji REST provides a RESTful API for writing data, again, from your application, whether it's on a browser or a mobile or a browser or an iPhone, for example, directly to Qiji in real time. And as we discussed earlier, in addition to allowing you to write data into Qiji, this REST interface allows you to read it back as well. The storage system that exists at the center of Qiji, we call Qiji Schema. Qiji Schema provides a layer of functionality on top of Cassandra and HBase. The data model for Qiji Schema I will discuss a little bit more later, but it's based on the data model of Bigtable, so it should be very familiar to anyone who's used Cassandra or HBase. We can think of it as having one row for every user of our application, and then within this row we have a number of columns containing all of the time series data that we've gathered about how users are interacting with our application, as well as other attributes about them like names, phone numbers, addresses, payment information, etc. The data scientists, as we discussed, need a way to query the data in Qiji. And again, they'll want to use languages they're familiar with. For this, we provide G Hive, which enables data scientists to use an SQL-like language to query all the customer data in Qiji Schema. Once a data scientist gets his data out of Qiji Schema, he or she can analyze it using, again, data science-friendly tools like R or Python. Then they can gain some insights about how customers are interacting with our application and hopefully apply those insights to develop some new predictive or machine learning models that will improve the customer experience for our application. Again, the data scientists could use R or Python to then train these machine learning models, but we run into the problem of those tools not scaling out to the massive amount of data we can store in a database like Cassandra. Certainly our application will be wildly successful, and we won't be able to handle that much data in R or Python. So a data scientist could choose to use Hadoop to train this model. In Qiji MR, we have a library of different predictive and machine learning models. So k-means, naive Bayes, item-item collaborative filtering, things like that. But again, this requires, so this is very powerful, and it's very flexible, but it requires the data scientists to be comfortable with Java, which is not usually the case, and anyone who's used Hadoop knows it's not the most user-friendly tool. So we provide another component, Qiji Express. This is one of the coolest components in Qiji. It's based on Scalding, which is an open source project from Twitter. And it provides a Scala-based DSL for describing chains of MapReduce computations. This is a very concise, intuitive way of describing these kinds of applications. You end up with programs that resemble a series of operations on the collections library in Scala. It's pretty similar in spirit to Spark, if anyone's used that. And this again provides a way to get a lot of the accessibility of tools like R and Python but still leverage the full flexibility and power of training your models using Hadoop. In any case, once we have one of these trained machine learning models, we now need a way to apply it. So in Kiji, we have a notion of a score. A score takes one of these trained machine learning models and some information we have about a customer and produces, and then applies the model over this customer information to produce some kind of result. Again, in our example, this would be a list of recommended products for a customer, but it could just as easily be anything else. Any other kind of prediction about the customer's behavior, for example. If the data scientist wants to apply these machine learning models in batch over all of the different users in our database, he can do so using Hadoop and KijiMR. But as we discussed, this is not the best approach. So instead, we provide mechanisms for implementing that kind of real-time, on-demand evaluation or scoring of models that we discussed earlier. So let's see how that works. First, we have a component called the Kiji model repository. So data scientists, as they build these new models and put them into scores, can upload scores to the model repository and make them live. Once we have a live score, let's say that, again, our user is interacting with our application. And the application sends a request via REST for the latest product recommendations for a given customer. This will cause Kiji scoring to trigger our score to generate a fresh recommendation. The score will request from Kiji schema the latest up-to-date information we have about a given customer. And after it does so, it will apply the machine learning model and then update and then produce a fresh recommendation that we can write to the database. After doing so, Kiji schema will send this data back via REST to the application. The application can render our recommendations for our customer. So this is really another one of the cooler aspects of Kiji. Provides a very elegant way for doing this kind of real-time scoring of trained machine learning models. And in the model repository, we also have a mechanism for handling all of these different versions of machine learning models that we'd want to use for things like running A/B testing, different experiments, and so on. And this provides a very smooth and elegant way for uploading these models, making them live, bringing them offline, and managing them. Finally, we have a notion of a freshness policy. So when we're doing this kind of real-time scoring with a machine learning model, we might not want to execute it every time our application asks for some kind of product recommendation or anything else about a customer. It might be the case if we're providing these recommendations based on what's in a customer's shopping cart, then we only need to produce new recommendations every time the contents of the customer's shopping cart change. Or we might just want to we might only want to produce new recommendations every hour or every 5 minutes. And so to this end, we have this notion of freshness policies that let you indicate how often you want to execute a score. So to recap, we talked about three different categories of functionality that we needed to build for our big data application. For getting data in and out of our database, in Kiji we have the Kiji REST and KijiMR components. For our data scientists to inspect the data in our database, gain some insights, and then develop and train predictive or machine learning models, we have G Hive, KijiMR, and Qiji Express. And finally, for applying these models and doing so in real time, we have the Kiji model repository and Kiji scoring. One final note about this framework, it's highly modular. So it might be that for some of you, you're building an application that looks something like what I've just described, but not exactly. So given the modular nature of Kiji, you can easily take whatever components are useful for you without having to use a big kind of monolithic project. And also, if you're building something that looks like this, but you need some kind of extra functionality, like maybe you want to do some kind of real-time analysis of these user events as they occur before they even get written to your database, you could easily write a component that uses Storm or Spark streaming or something like that and incorporate it. OK, so hopefully that gives everybody some idea of the problem we're trying to solve and then how Kiji goes about solving it with this modular framework. Now I'll talk about the Kiji data model and how we map that data model onto Cassandra. The Kiji data model is very similar to Bigtable. So again, it's going to be really similar to what you get in Cassandra or in HBase. We store all of our data in tables. The tables consist of rows. And rows consist of some kind of row key as well as data. In Kiji, we call this row key an entity ID. We support composite entity IDs. And these entity IDs can have hashed and unhashed components. You can use hash components to determine how you spread your data among different replica nodes in the case of Cassandra. And the unhashed components you can use to control how data is ordered on disk for doing scans. For anyone who's used Cassandra, this is, again, really similar to the notion of partition keys and clustering, or partition columns and clustering columns. The data is organized into different column families. Within column families, we have columns. We call these, we refer to the column names as qualifiers. Again, this is the same as Bigtable. And where our data model diverges, so again, so far this has been pretty similar to what you get in Cassandra. Our data model differs somewhat from Cassandra in that we have built-in support for time series data. In Cassandra, if you're storing time series data, you'll probably add one clustering column somewhere in your definition of your column family with a timestamp in it. Whereas in Kiji, we provide native support for the notion of timestamp versions of different columns. And again, this is taken from Bigtable. Finally, the data we store in every column consists of complex data types. We use Avro here for serializing and deserializing the data that we store in Cassandra. Avro is another one of the open source projects that I referenced earlier in the talk. So rather than just storing like a single string or a single integer in a column, you can store these complex types that can consist of maps and lists and nested versions of these and enumerated types. Finally, we have a notion of locality groups in Kiji. Again, these are taken from Bigtable, and they allow a user, when he specifies the layout of his table, to group together column families that are accessed together and that we'd like to have stored on disk together. So let's say, for example, we're building an application and we have some set of column families that we're only going to access for some kind of batch jobs. And we also have a set of column families that we'll access only for some kind of real-time operation. That'd be sensible then. So we probably want to store these separately. We might want to have some different attributes for them, whether they're cached, for example, whether they're compressed. And to do so, we can specify different locality groups and then put all of our batch column families in one, all of our real-time ones in another, and then specify attributes like the batch stuff we might want to keep compressed and on disk. And the real-time column families we probably want to keep cached, for example. So these locality groups give us a nice separation between how we want to organize our data logically in column families and columns and how we wish to organize it physically on disk with locality groups. Finally, in Kiji, we have the notion of a row as the unit of transactional consistency. So we support atomic reads and compares and sets across rows. So now I'll talk about how we map this data model onto Cassandra. To begin with, we map locality groups to column families. This makes sense, and those of you, using Cassandra know that we, a given column family, we store contiguously on disk. So mapping a locality group to a column family makes sense. Then the entity ID we map to the primary key of our column family. So the hashed components become the partition columns, and the unhashed components become clustering columns. Likewise, the family, the qualifier, and the version, we also map to clustering columns. And finally, the data that we store in Cassandra, we store as blobs because we're using Avro to serialize all the data that we're storing. To give another look at how this Kiji to Cassandra mapping goes, this is my artist's interpretation of a single row with a couple column families in Cassandra. So here we can see the hashed component of one of our entity IDs. We map to the row key for our Cassandra row. And this will determine what replica node it goes on and so on. And all of those clustering columns we described, as those of you who worked a lot with CQL are familiar, those get mapped to composite column names in Cassandra. So again, we'll see everything ordered by first the unhashed components of our entity ID, and then the column family, the column name, and the timestamp. And if we had a couple of different locality groups in our Kiji table, then here we'd have a couple of column families in Cassandra. So a few implementation notes on how we built the Cassandra version of Kiji. We used the DataStax Java driver. So we did 100% of the implementation with this. We didn't use the Thrift API at all. We built it on top of Cassandra 2.0.6. I think 2.0.7 just came out, so probably upgrade soon. We made pretty extensive use of the async API in the Java driver, which was pretty awesome, and I'll describe why we need that in a minute. We also built a new MapReduce input format that has a number of features that weren't present in the stock input format that comes with Cassandra, mainly because we need to support Hadoop too. But there are a couple other things we added as well. So now let's talk about some of the issues with this mapping and how we've addressed them. The biggest issue is that Kiji allows us to allows operations that operate at the same time on multiple locality groups. So we can have and remember this locality group in Kiji, which can contain multiple tables or multiple column families, maps to a single column family in Cassandra. So if we have a read in Kiji that goes across multiple locality groups in the same row, that means we need to have a read in Cassandra that goes across multiple column families. Oops. Yes. And to implement this, we just have to issue multiple reads in Cassandra, since there's no mechanism to read from multiple column families at the same time. And this is one instance of where the async API in the Java driver really came in handy, because we'd issue a lot of reads really quickly and get the results back together. This is also one of the reasons that we had to develop a new Hadoop input format, because we needed to support in our MapReduce jobs being able to issue multiple reads and then combine them in our record reader. Another tricky one is a compare and set that crosses locality groups. So again, when you're designing your Kiji table, you probably want to put, you're going to put data that's typically accessed together in a single locality group. So this shouldn't happen very often, but we allow for it in Kiji. And for this, there's really no solution we could come up with, since we didn't want to use Zookeeper or something like that to provide locks on every single row in our Kiji table. So in the Kiji implementation of Cassandra, we don't allow these comparison sets that cross locality groups. And finally, in general, we've sacrificed some of this transactional consistency in a single Kiji row. We still have it for a single locality group, but if you do a read to a row in Kiji, in the meantime, someone could issue a write to one of those locality groups, or someone could issue a write to multiple locality groups, and your results could be, you could have the old data for one locality group and the new data for another. So this is something that we've just chosen to sacrifice in the notion of better performance. Another issue is filters. So HBase provides a very rich set of user-defined server-side filters. The kind of equivalent in CQL is to use where clauses in your CQL queries. And these allow for fairly rich filtering, but it's not quite as powerful as what we get in HBase. So if a user in a Kiji data request chooses to filter based on some timestamp range or some column qualifier range, those we can translate to where clauses pretty easily. But if a user has a request in which he specifies a regular expression on a column qualifier, for example, in that case, we just have to do the filtering on the client side. So we started looking at some ways to do more of this filtering on the server in Cassandra. If anyone here has any suggestions, I'd love to talk to you after the talk. But for now, we just issue some of this filtering on the client and really just have to educate our users about what kind of filters are very efficient and what aren't. Finally, there's an interesting difference in how we translate these entity IDs with hashed and unhashed components in the HBase version of Kiji versus the Cassandra version of Kiji. So let's say that we've defined an entity ID for our application with the state and the city and the name of our users. Maybe we choose to hash the city and state. So we want to distribute our data among all of our replica nodes based on the city and state a user's in. And then we leave the username unhashed so that we want to be able to perform scans over users who are in the same city. In the HBase implementation of Kiji, we map this entire entity ID to the HBase row key. In HBase, the row keys are just byte arrays, so we can hash some components of the entity ID, leave some of them unhashed. And HBase will order all of this data in lexicographic order of the entity ID. In Cassandra, on the other hand, we get very wide rows. Remember, we're mapping these unhashed components of the entity ID to the clustering columns in Cassandra. So we end up with rows that are, so the rows are dictated by the hash components, which map to our partitioning columns. And then the rest of the entity ID maps these clustering columns. And this gives us the functionality that we want, because we can now perform a scan through all of the different users who live in the same city and state. But it does provide some limitations that our users need to be aware of. Namely, that we could run into limits on the size of one of these wide rows, which I believe contain 2 billion elements in them. So this, again, is not a big issue, but it's just something that users of the Cassandra version of Kiji need to be aware of. Yes. All right, so the status of the project. We have an alpha version of Kiji schema that's available now. This URL is a little long, so I'll send this out to the list or post it on the website for the meetup. But you can download this now. We have a version of our Kiji bento box that supports Cassandra. So you can download a tarball, just unpack it, run one command, and have a working cluster locally on your machine with Hadoop, Zookeeper, and Cassandra. We have a little tutorial that lets you build a phone book that uses a Cassandra Kiji table. So you can write data to it, read it back, delete entries, and so on. Over the next quarter, we'll add support for all of the other components in the Kiji ecosystem to run on top of Cassandra. Now, the majority of the work in modifying Kiji to work on top of Cassandra was building this Cassandra version of Kiji schema. In particular, in the next quarter, we're going to concentrate on producing a Cassandra version of Qiji Express. Again, this is a really neat tool that lets you very easily build complicated chains of MapReduce jobs. Finally, we'll begin to expose some of the Cassandra-specific features to Kiji users. For example, to allow them when they're issuing reads or writes to specify consistency levels. So to recap, we talked about 3 things you need to do to build a big data application. The first was to have a way to get data in and out of your database from your application. And to this end, we have Kiji RESTs and Kiji MapReduce. The second was to enable your data scientists to inspect the data in Kiji and then use it to gain some insights and develop and train some machine learning models. For this, we have G Hive, Kiji MapReduce, and Qiji Express. And then finally, we need a way to apply these models in real time, to manage all the models that our data scientists are building, to be able to deploy them online, manage which ones are active and which ones are not. And for this, we have the model repository and Kiji scoring. So just to wrap up, I want to say thanks to the Cassandra community. For newbies like me to Cassandra, it was really useful to have all of this information online. Everybody who's on the mailing list for developers and users were really helpful, especially as we were developing this new Hadoop input format for Cassandra. And also just the amount of videos and slides and so on that were online from events like this made it really easy to get up to speed quickly. Finally, if you want to get started and try it now, the first URL, you can get access to a fully functional bento box and lots of tutorials and user guides for all of the components I just described. And the second URL is for the Cassandra version of the bento box, which has support for schema and a Cassandra-specific tutorial.